Hello there, welcome back to Decaf-Math ASMR, and a very warm welcome if you are new here. Today, let's take a look at polar coordinates. I think I've made a video in the past on polar coordinates, but 0, our origin, to our x comma y. So we go from this 0 to that line. And so theta is one of our parameters, kind of like x and y are parameters. Theta is one of them, and the other one is this length, the length of the segment, which we'll call r. And it's r because it's like having the radius of a circle. So actually, I think I have a compass right here. So it's like measuring this distance and making it my r, the radius of my circle. Like that. I'm not going to draw it all the way out, but you get the idea. This distance would become my radius, and having this angle would be just sweeping out this much of it. And so now we have two different parameters. Instead of left and right, up and down, we now have a radius, which could be, shorter, farther. It's the distance from the origin to our point, here to here, here to here, here to here. That length is our r, and the theta is the angle from my 0 to, if it's a positive theta, which we'll get into if it's negative, but we go positive from 0 going this way, so that would be counterclockwise, right? This way up to that line, and that would be theta. So we have x, y, and we also have r comma theta. So when we introduce a new system like this, of course it seems like it would be handy to be able to convert between the two. So this is our polar coordinates. This is our Cartesian or rectangular coordinates. Cartesian or rectangular coordinates, and they are related to each other. So let's look at how they are related. Well, with this picture, actually, we might recognize some of our unit circle work in trigonometry. This looks really similar. If the radius, if r is specifically 1, then we have the unit circle. But here we just have r as any length or distance. But we can kind of repeat some of our SOHCAHTOA work. SOHCAHTOA, that's our sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent, right? SOHCAHTOA. SOHCAHTOA. Sine opposite hypotenuse, cosine adjacent hypotenuse, tangent opposite over adjacent. So I actually can take this point here and make a right triangle here, here, here. So the hypotenuse of this right triangle is going to be r. So whenever we apply SOHCAHTOA, it's going to have to be on a right triangle. And we know that the length of this leg is going to be x. This is going to be x because we know it's x comma y. X being x to the right here from 0 to here. And this is going to be up y. So this leg is x, this leg is y, and the hypotenuse is r. And so to convert between Cartesian and polar, we're just going to look at SOHCAHTOA a bit. But before we write out the SOHCAHTOA relationships, let's also note that this is the Pythagorean theorem, or we can use the Pythagorean theorem rather, because this is a right triangle. And the Pythagorean theorem tells us that the sum of the square of the not hypotenuse side equals the square of the hypotenuse side, or the length of the hypotenuse. So we would have x squared plus y squared equals r squared. So that's one way to relate x, y, and r. Now usually when you solve something like this, if you had like r squared equals 16 for instance, then r would be plus or minus the square root of 16, which is 4. So r could be positive 4 or negative 4, because negative 4 squared, in parentheses, is also positive. But in this case, usually we just start with a positive r first. But I'll write both for now, and we'll get into what the positive and negative parts mean. So we do the plus or minus square root of x squared plus y squared if we define r as the radius of a circle. Then we'll just keep the positive square root of x squared plus y squared, and we usually start with that. But we do have to interpret the positive and negative parts, so we'll get into that in a second. But this is how x, y, and r are related, so let's keep that in mind. Then to relate thetas, we have SOHCAHTOA. So sine is opposite. So sine of theta is the length of the side that's opposite of that angle. So that would be y over the hypotenuse, so r. Which means if we rearrange that, we multiply the r over. That would mean that y equals r sine theta. And similarly, cosine is adjacent over hypotenuse, so x over r. Remember, our trig functions help us relate an angle to lengths of sides, ratios of lengths of sides. So rearranging this, I multiply by r on both sides. I would get x equals r cosine theta. And lastly, we have tangent, which is opposite over adjacent. So we have tangent theta equals y over x, like so. So now we have some formulas that help us relate x, y, and r. We have r is this, plus or minus square root of x squared plus y squared. We have x equals r cosine theta, y is r sine theta, and tangent theta equals y over x, which means that if we have x and y coordinates, say 3, 2, we can take the inverse tangent of my y value over my x value and get a theta. Again though, we have to actually interpret the two values that we get. So based on this theta and based on this r, we need to actually be able to place where that r comma theta is on this circle and make sure that it corresponds to the actual x comma y that we're looking at. So my point is just that beyond just these formulas, we need to be able to actually interpret r and theta. So I were to plug in the square root of 3 squared plus 2 squared to get 9 plus 4 is the square root of 13, right? Positive square root of 13, and then a positive angle here would place this. So I would do the square root of 13, comma, and then tangent inverse of 3 or 2 over 3 y over x, right? So I'd have a positive angle there. But if I were to have a negative r with that same angle, that actually reflects it over here. So 3 comma 2, it would be over here like this. Like so. So what that means is, so this would be theta as well. So this is where it gets kind of confusing. Even within one time around the circle, we can go from 0 to 2 pi radians, right, or 360 degrees, and we can go positive this way, but we can also go negative of an angle, so it would be going this way, it would be clockwise. So that's kind of tricky. And so because we have a positive angle and a negative angle, so just to get back to this point, right, if this were theta, if I moved this way, let me see if I can sketch this out. If I moved, I can start from 0 and go all the way around to that angle, which is my 2 pi or 360 degrees minus this theta, because that's going from here and cutting out and stopping there. Same as 2 pi minus just that much. That alone is the same point. So I'll write out an example of this here in a second, but if, let's say, r, well, we said it was square root of 13, right? So square root of 13, comma, whatever that angle is. If I did square root of 13, comma, 2 pi minus that angle, I would also get the same point. So that's the idea of a negative angle. But we can also have a negative r, which is so bizarre, but that is flipping it over to here. So if I have a negative r, so if this was positive square root of 13 and this is negative square root of 13, we can actually have a negative r here, but then we would flip back to this negative angle idea to bring it back here. So if somehow I had my angle here up to this point, so the angle kind of tells you the location, right? The angle that traces is kind of the location, which side you're on. But if I can trace out the angle to here and then do a negative r, it would flip it back to here. Some strange reflection stuff going on. But we can find this angle in the positive theta as well, and then do a negative this xy thing. And really, just a quick little sketch is fine. It doesn't really need to be perfect. Unless you have a compass with you, it could be helpful to sketch that out, but we really don't need to. But let's say we have a point, but now we're talking about polar coordinates, right? So let's say we have 2, so we know that this is a length of 2 now. And this angle, I guess it looks like a pi over 3 to me. That's good enough. So let's say in polar coordinates we have 2 comma pi over 3. So it's our r and our theta. So let's now do a couple of calculations here. Maybe the 4 pairs. So this is one of them, 2 comma pi over 3. That give us the same xy coordinates. So if I were to try to find what those xy coordinates are in the first place, I guess we can calculate that first. We have r and we have theta. So we know that x is going to be r, which is 2 cosine theta, which is pi over 3. And pi over 3 radians is a special angle, right, or 60 degrees. So cosine of 60 degrees is 1/2. Very good. So 2 times 1/2. This would be 1, right? And then y is r, which is 2 sine pi over 3, which is root 3 over 2. It's one of our special angles also. Times 2 is root 3. So 1 comma root 3. So that means that I sketched this a little off. If I were to just use equal scales, 1, 1, 1, 1. It's a little bit off because that would mean x is 1 and y would have to be more than 1. This is like 1.7 something, right? So technically this looks more like a longer x and a shorter y, so it's okay though. I could just change the axes here, or I can just shorten this too. Or I can make the angle a little bit larger. I don't know. Why did I calculate this? I don't know, but whatever. Okay, so something like, and it would have to be a little bit longer here, so how about we just go up a little bit. Actually, I'm silly because pi over 3 is bigger than pi over 4, so it actually should be up here more. That's why it's good to always check your work. Just kind of check your intuition. Pi over 4 is halfway to the pi over 2, so pi over 3 is a little bit bigger, so that actually looks better. Okay, so this is my pi over 3. Hopefully, I'll make a note of this in the description box. Correct myself. Okay, so like this. So now we know the x-coordinate is 1, the y-coordinate is root 3. But the point here is to emphasize the reflections and how to write out the different pairings here within negative 2 pi to 2 pi, just to give you a feel for this reflection stuff. So for 1, we have 2 comma pi over 3 in polar. And so the x comma y, like we said, is 1 comma root 3 x comma y. So other polar coordinate pairings that give me the same 1 comma 3, for instance, would be taking this pi over 3 angle and going the other way. So negative. This is going to get kind of confusing drawing it all on one, but to give you a feel for it, we have pi over 3, which is this bit here. This going negative, but with the same positive r, would give me the same xy as well. So going this way would be 2 pi minus pi over 3, which keeping the common denominator, so this would be 6 pi minus pi is 5 pi over 3. So with the positive r, so 2 comma 5 pi over 3, that would also, or should also, give me the same 1 comma root 3. And you can check that by trying out 2 cosine 5 pi over 3 and 2 sine 5 pi over 3, negative, rather. Because we're going the other direction. So I should have done either negative 2 pi minus pi over 3, that would be negative, or pi over 3 minus 2 pi. Okay, so we have 2 comma negative 5 pi over 3, that would be going counterclockwise. Going clockwise, it's positive pi over 3, and those are with our positive r's. Now if we flip this over, we reflect it over here with exactly a distance of 2 as well. This would be an r of negative 2. Okay, well, it's not just negative 2, it's relative to the angle that we're looking at. So theoretically it could be positive 2 if we're looking at this point, but if we're trying to flip it back to this, then we want a negative 2 with an angle that brings me here, because if the angle brings me to this point, or this line, this angle, right, so it's always from 0 going counterclockwise to the segment. If we go to this part, then we reflect it back, it would go back here. So this angle with a negative 2r would also give me an equivalent pairing for 1 comma root 3. So that angle would be what? It would be a pi over 3 plus another pi. So again, keeping a common denominator, so that would be 3 pi over 3. So it would be 4 pi over 3 going this way, like so. So the 4 pi over 3 would take me to this, and then my negative 2 would flip me back to this. And so then the last one would be to go negative angle and negative r. So that would be here, and that would just be, you can look at this however you want to, but you could do 2 pi minus this angle, 4 pi over 3, and go negative this way. So that would be negative, and remember this angle would be negative because you're going clockwise, so it would still be a negative 2 comma if this is 4 pi over 3, you do 2 pi minus that, so that would be 2 pi over 3 with the negative. Let me write that better, negative. Okay, so I'm gonna write out all 4. Promise, we're kind of sketching it here. But the idea is we can do a positive r and have a counterclockwise and a clockwise angle. So a positive r with a positive angle and a negative angle. And then we can have a negative r that will take us here, which would reflect us back here. So to get this angle also has a counterclockwise and a clockwise angle, so one positive and one negative. And so even within just negative 2 have a positive r with a negative, negative theta. And then we have a negative r with a positive theta. And a negative r with a negative theta. Negative 2 pi over 3. Okay, so that kind of starts giving you an idea there. It's all about reflections. So when you talk about positive and negative thetas, you're talking about moving either counterclockwise or clockwise. Positive is counterclockwise, starting from 0, going this way, and clockwise is starting from 0 and going this way, which would be negative. And then when you talk about positive and negative r's, you're talking about reflecting relative to those angles. Okay, so I know that the writing was kind of horrible. There are a lot of traffic noises outside. I'm doing my best. But I do hope that this hopefully starts building some intuition here. And all of this really applies when we're trying to go from rectangular to a pair of polar coordinates. But like we said,